Swayam Prabha. Digital India. Educated India.
Alright, so these are some questions which are very simple based on our previous lectures, and I shall now keep raising these questions, popping them at the end or beginning of every lecture, just to take a recap of the concepts that I have taught. And these are going to be simple short questions, either conceptual or numerical. So, I would suggest that you take a pause, attempt these questions quickly. I would strongly suggest that you first solve it yourself and then go to the next slide to get the answers. So, for the single degree of freedom system, in the undamped vibration case, we have seen that the response is obtained by an expression which we derived as x of t equal to capital X cos omega n t minus phi I. This capital X, we have seen that it is a function of the initial conditions that we impose. That is, supposing that you have a simple spring mass system, damping being ignored, we are having stiffness and mass as the two elements of the vibratory system. Now, in this case, from its mean equilibrium position, if we disturb this with either initial displacement x naught or initial velocity v naught, that is the velocity given to the inertial mass at t is equal to 0, that is how we define initial displacement and initial velocity. And then after t more than 0, that means these conditions are imposed exactly at t is equal to 0, and after that there is no external stimulus to the system, and the system is allowed to vibrate on its own once these initial disturbance is imposed. Now, as we see here that the amplitude of the response is given by an expression which is given here. It is a function of the initial conditions, that is x naught and v naught, and of course, omega n embodies the properties of the system k and m. What you notice here is the fact that the response x as a function of time is a harmonic response, right. So, it has certain magnitude, it has certain amplitude capital X, and that response varies harmonically given by this cosine term. The frequency with which the oscillations happen is the natural frequency of the system omega n, and there is some phase lag. Okay. So, this phase lag, as I mentioned, we would call this as initial phase lag, just to distinguish it from another term phase which we shall see in case of the forced vibration. So, we call this as initial phase lag. Now, what I mentioned to you is that it depends either on x, I mean the initial amplitude x naught and v naught. So, suppose this capital X, the amplitude with which it vibrates depends either on x naught or on v naught or both in fact. So, it can be a function of both. So, generally we either have initial displacement or initial velocity. For example, as I mentioned, if we treat a guitar string fixed at both ends as a vibratory system, and if we plug this guitar string at t is equal to 0 and then release it. So, this is the initial displacement that we impose, and then when it is released from that initially displaced position, it continues to vibrate as the time goes by. Whereas, we may have the same string like in santur musical instrument, where we strike it. So, the fork or the tongue basically strikes the string, precisely that also happens in piano. So, when you strike it with certain velocity, that basically becomes the initial velocity condition. In general, we may say that it would also you may have initial displacement and initial velocities as the two initial conditions, and then the amplitude with which it will oscillate depends upon both of these values for a given vibratory system. Now, it would be interesting to now see if we displace this vibratory system from its mean equilibrium position with initial displacement, let us say x naught. Okay. So, if I pull this mass and if x is treated positive downwards in this case. So, let us say this is at time t is equal to 0, we have displaced it by x naught, but we simply release it from that displaced position. The spring is stretched up to this point, and now when you release it, it will have the response governed by this particular expression. What will be capital X in this case? Because initial velocity is not imposed, this term is 0, and obviously capital X will be small x naught, that is the initial displacement. And you can notice that if V naught is equal to 0, initial velocity being 0, this phi I tan inverse of 0. So, phi I is going to be 0, which means that this expression will turn out to be x naught cos omega n t, simply x of t is equal to x naught cos omega n t, and which actually means that if I plot x positive downwards in this graph as well, then this is the initial displacement that I will impose, and then you will have a cosines curve being plotted here. Okay. So, the amplitude will be x naught, and it executes a cosine function, which is expected, because physically if you notice, if you have stretched it to x naught and then released it, the mass is going to move like this. The mass is going to move like this, it is going to go on the other side of the mean equilibrium position, and it will keep on oscillating. That is how it happens when you have initial conditions as initial displacement. Suppose instead of initial displacement, if I hit it with an impulse which induces initial velocity V naught, then this is applied at time t is equal to 0 when there is no motion. Okay. So, the mass is stationary and x naught is measured from this mean equilibrium position, and then what you will have is a condition where x naught is 0. So, this is the condition where x naught is 0 and V at t is equal to 0 is some initial velocity with which I hit the mass, or I induce initial velocity to the mass equal to V naught. Now, obviously, you may notice that x in this particular case is going to be, this x naught is going to be 0, whereas the second term stays, and then capital X is going to be V naught by omega n. What would be phi I? It is going to be tan inverse of V naught by x naught. X naught is 0. So, tan inverse infinity is going to give you the phase lag, initial phase lag of 90 degrees. Now, if you substitute that in this expression, then your capital x of t is going to be V naught by omega n, that is your capital X, cos omega n t minus pi by 2 will turn to sin omega n t. Okay. So, that you can expect, do not you? I mean, if we basically have an impulse given at the stationary position at the initial position of the mass, the equilibrium position of the mass, and if I hit it, I expect the response to be like this. So, that means the response is going to be sinusoidal. Okay. I have not plotted the time properly, but you can imagine that this is the harmonic time function. In this case of initial velocity will follow the sine curve, right. So, a harmonic function of time for a given system having natural frequency omega n. Whether it follows a cosine function or sine function depending upon the initial conditions, what is clear that the frequency with which it will oscillate about its mean equilibrium position is going to be the natural frequency of the system, and that is undamped natural frequency of the system, which is dependent on the stiffness and mass of the system. The amplitude of course, in this particular case is V naught by omega n. As a general case, the response amplitude capital X is going to be dependent on both x naught and V naught. So, you may have a situation when both of them are non-zero, that it might oscillate like this. Okay. So, it will start with some value which is going to be a function of both x naught and V naught. Okay. Amplitude of course, will be governed by that. The time period of oscillation which is given by this distance between two consecutive peaks, because what we plot here is typically the time period of oscillation, and that period of oscillation all of us are aware is equal to 2 pi over omega n, right. So, if omega n is your natural frequency of oscillation, then the period of oscillation is going to be 2 pi over omega n, and that is how the free vibration response in the undamped case would happen. And so, if you are interested in finding out the response at any instant of time for a system which is perturbed or disturbed from its mean position, this is the expression that you can use. It is completely defined when you have a fully defined initial conditions like x naught and V naught. And so, if those two conditions are known, and if you know your system in the sense you know your k, you know your m mass of the system, then you completely know the dynamic response to initial disturbance. Now, it looks the response to be in practical situation, how would it happen that you have an initial condition like x naught and V naught, where will it come from? So, we might have couple of examples to discuss, and therein you will understand what this x naught and V naught would mean, okay, when you are analyzing the vibratory systems response. Obviously, most of our mechanical systems they have all the time some kind of a forcing function. So, mostly the vibration response will be forced vibration response, but we would eventually use these expressions which we have derived in analyzing vibration response to some arbitrary excitations, and therefore, these expressions which apparently looks relatively not so useful, or in the context of all mechanical system being subjected to harmonic or periodic forcing function. However, these expressions are very important in the larger context of vibration response. Okay, so, typically when we first derive these governing equation of motion m x double dot plus k x equal to 0, you remember that the system of course was a horizontal system like this, and the mass is oscillating in a frictionless surface, and we said that okay, x is measured from an equilibrium position here, and it simply oscillated around this mean equilibrium position. Suppose we have a system oriented like this, and all the time we have been saying that this is the mean equilibrium position, and our x is measured either vertically up or down positive, and it oscillates like this. Okay. So, when we look at the free body diagram and we consider this mass isolated from surrounding, we say that okay, if the mass moves down, the restoring force because of the spring will try to pull the mass up if it tries to go down, and the force is proportional to the displacement, and that in turn is the stretch in the spring. So, as the spring gets stretched more and more, so as x increases, the restoring force k x obviously increases. Okay. And so, if we apply the Newton's law, m x double dot equal to f, which actually means if your x is going down, minus k x is the force, and therefore, the equation that we get is m x double dot plus k x equal to 0. Now, a typical question that is asked is, where is the gravity force gone? Okay. Because of the gravity, the force mg should act, and we should consider mg into the forces which are acting on the mass. The way we have considered the spring force, why not also account for the gravity? And that is the usual confusion or a problem which is faced. So, the reason why we have not accounted for mg is for this reason, that supposing the spring is just hanging like this without the mass being attached, and this is your position of the end of the spring, and now if you attach this mass to the spring, because of the weight of the mass, the spring gets stretched, and now the new position of this mass is going to be here the moment the mass is attached. This deflection, all of us are aware, is the static deflection, or the deflection when the mass is not moving, it is gently put or gently connected to the end of the spring, and the mass simply pushes down, and during that motion the gravity is acting on the spring and the spring gets stretched. So, the delta is the displacement or a stretch in the spring due to gravity loading. All right. So, if you measure the displacements with this initial position of the spring just before the mass is attached to the spring, if this is considered as your x of t, then obviously you will have to include the gravity as an additional force. Okay. But if we attach the mass and the mass slides to this position, and the gravity being a constant force, it is going to settle down at a particular position delta from this equilibrium from this particular initial reference point, then the mass is going to be stationary at this point, and afterwards when we apply these initial conditions to the mean equilibrium position of this mass, then the mass is going to oscillate. Okay. So, suppose we describe this motion beyond or about this new equilibrium position of the spring mass system. This is the equilibrium position just before the mass is attached to the end of the spring. So, now if we try to write the governing equation of motion or generate the governing equation of motion, then now if we try to get the governing equation of motion let us say about this point, then you will have to consider the gravity. Okay. So, now how you do that is this mass would be moving with respect to this reference point, and therefore, that motion is going to be delta plus y. Okay. So, that is basically is going to be your motion with respect to this reference point, and in that case then definitely the gravity would act and will have to be accounted for. And the restoring force now in this case is going to be k into delta plus y, and of course, y means y of t. So, now if you apply the Newton's second law, sorry, this is going to be mass times the acceleration, which is going to be second derivative of this response term, delta being constant is going to be m y double dot will be equal to all the forces which are going to act on it. So, k into this is of course negative, because all the displacement velocities and accelerations are downward positive. So, k into delta plus y and minus plus m g, because m g is acting in the direction where we have taken y and x all positive downwards. So, now if I rearrange this m y double dot plus k into y, if I keep minus k into delta on the right hand side itself and then plus m g, this is how I get it. Now, you may notice that k into delta in a static condition is the restoring force which is proportional to the stretch because of m g acting on it, right. So, with that logic, the gravity is going to be equal to k into delta, because the stiffness multiplied by the stretch, initial stretch, because of the presence of the gravity loading is going to be generating the forces which are going to get balanced out, right. So, therefore, m g being equal to k into delta, the right hand side term just turns out to be 0, and that is the reason why if we are considering the dynamic response or motion with respect to the equilibrium position of the mass, and if this equilibrium position pertains to the static deflection, then you do not have to account for the gravity, but if you measure it with respect to the initial reference point when the mass is attached to the spring, then obviously you will include the gravity, but then you have to account for, or you have to take the displacement with respect to this initial reference point. Incidentally, now since we have found that the natural frequency of oscillation for an undamped system is given by square root of k over m, you can get the alternate expression of k over m as g over delta, and therefore, the expression for the natural frequency is also square root of g over delta. Okay. So, if you know a heavy machine, if you mount on the isolators, okay, and if you measure, once this heavy machinery is lowered onto these isolators, and if you can measure the sag, static deflection or a static sag of this whole machine on these isolators, if you can measure that delta, then you can find out the natural frequency of the system without knowing the mass or the isolator stiffness. Okay. That is the advantage of this expression. So, if you lower down a heavy machinery on the isolators and have somehow manage to get this delta measured, then you can find out the natural frequency of the system. Okay. Now, so we have discussed this part, amplitude and frequency of vibration. Amplitude is constant, which is very important to note that when the system does not have damping, the system, when it is perturbed with some initial displacement or initial conditions, it continues to vibrate without any change in its amplitude. This amplitude remains the same what it is at t is equal to 0. So, no dissipation in the system, and therefore, the energy at each cycle is same, and therefore, the amplitude remains same throughout. Okay. Of course, is a hypothetical case, because we know that even if there is no formal damping mechanism like a dashpot in the system, there will always be some mechanisms or some system means of dissipation. The simplest is that unless you put the vibratory system in a vacuum, there will be aerodynamic damping. Okay. There will be friction in the material of the spring or any structural member which is vibrating. So, that would create a reduction in the amplitude over time. So, as we progress, that is something which we will discuss shortly. Okay. And what we saw is, if this is the amplitude which is a function of these initial conditions, the frequency which is inverse of this time, frequency in terms of cycles per second is 1 over t. So, that is in practice, this is a common unit of frequency of vibration, cycles per second or hertz, that is 1 over the time period of oscillation. Now, before we look into the damped vibration case, let us take an example here of a simple vibratory system. The job is to find out the natural frequency of the system, and so this is a rectangular beam which is fixed in the wall, and at the end of this beam you have a hoisting drum, as you can notice in the side view. That drum is lowering a mass, or it may be lifting a load from the ground, and we are supposed to explore this system for its natural period of vibration. Okay. How would you model this? Now, if you recollect, our entire vibration analysis process first step is to convert this physical system, which is being represented here, into a corresponding vibratory system. So, a simplified model has to be built before we analyze the system. Now, it looks apparently little complicated to figure out how do I convert this into a vibratory model, and as I have been saying all the time, that that first step is really the most critical and challenging step, but that step will become easier as we go along and as you solve many problems. What we need to now make few assumptions here. First is, this beam is small enough in terms of its cross section. So, this is the rectangular beam that I am talking about, and if you have a heavy mass which is being lowered from here. So, obviously, the flexible element in this entire vibratory system or entire system, we may assume that the beam is the stiffness, or beam is the compliant member in the whole setup. Okay. So, you all know a cantilever with an end mass or a force which is acting here. How do I get the flexibility or the stiffness of a cantilever? Okay. So, I will have to model now this beam as a stiffness element. So, my first simplified model is going to represent this beam as a spring element. And you all know, go back to your solid mechanics strength of material books, you can find out the relationship of delta, the deflection at the tip where the force is being applied as if this force is F, let us say, right. So, which gives me force over delta, which is K, the stiffness as 3 E I over L cube, right. So, based on the flexural rigidity of the system, E is the Young's modulus, I is the area moment of inertia, and obviously because the cantilever is bending about this axis, we will have to take area moment of inertia of that rectangle 1 over 12 B d cube, where B is the width of this cross section and D is the thickness here. Okay. So, it is all straightforward to find the stiffness of this particular structural member. Okay. L is the length of this cantilever. So, once it is done, we basically get the numeric value of the parameter of the vibratory system, the K, the stiffness. But that is not the only system here. You have a winch, sort of a pulley, which is lowering the mass. The mass itself is quite substantial in the sense that we may have to again make assumptions. It is all about making assumptions and getting on by capturing the system in its simplified vibratory form. So, another assumption that I make here is that I will treat this pulley to be massless. Okay. We shall look at what happens if this pulley is not considered massless, and it is actually not massless as such, but compared to the mass which is being lowered from here, if this mass of the pulley is let us say 100 kgs and the mass being lowered is let us say 1000 kgs, then we may as a first approximation consider this to be massless. So, that means the mass of the pulley is relatively small as compared to the mass being lowered. It is also important that the first assumption was that the cantilever is contributing to the stiffness property, but not to the mass property. That means, I am also assuming that this particular member is massless or having mass which is substantially smaller than the mass which is being lowered here. Of course, these are all assumptions and they do have influence on the output that you get, but these are all engineering assumptions. You have to make assumptions to arrive at solutions, right. So, it will influence the results, but if we know what we are doing, we can refine our solution process, we can refine our model to come at a more accurate solution. Each step towards more accurate solution involves making a model more complex, more involved and lengthier. So, it is all with certain assumptions we will get the natural frequency of the system. So, presuming that the mass of this cantilever and the mass of this pulley and the entire winch system there is comparatively smaller as compared to the mass being lowered, then we can complete the modeling of the remaining part. What is the remaining part? This beam was considered to be a spring, and assuming that this is massless, can we attach this mass at this end to complete the model? It all depends again. So, this rope is a small diameter wire rope and it is being used to suspend the mass at the end of it, that is this mass, and no matter what, even if this is a steel rope, it will stretch. Okay. It has its own flexibility. So, it is prudent to consider the rope itself as a spring. So, you all know that a thin cylindrical piece itself has its own stiffness. So, if it is subjected to tensile loading, delta is PL by AE, where A is the cross sectional area of the rope or of this particular member. If it is circular, that area is going to be pi by 4 into diameter square, and so this cross sectional area is of the wire or any cylindrical specimen. If it is square, you will have accordingly area being replaced. E is the Young's modulus of the material the wire is made up of. So, if if the rope here is made of steel, you will have appropriate value to be used for this E. L is the length. So, if I denote this as capital L, then I can use this capital L of the wire as the parameter here, and F or P in this case is the load being applied here. Okay. Now, of course, the load being applied is going to be the load which is suspended from this wire. So, once you know this, I can find out K, which is nothing but P over delta, as we have found in the previous case, is AE over L. So, for a uniaxial member like this, a cylindrical wire rope, AE over L is the stiffness of this wire rope. So, instead of using this mass or using or attaching this mass at the end of this cantilever, what I would now do is I will use the spring representing the rope. So, I will call this as Kr and this as Kb, and this Kb in my case is going to be 3 EI by L cube, the stiffness of the beam, and Kr is the stiffness of the wire rope. And now, at the end, because these two springs are in series, because you can see that this end of the beam is essentially connected to the wire rope. Okay. So, these two springs Kb and Kr will be in series, because the extension of this mass, because of the flexibility in the wire rope, happens independent of the deflection in the beam. Even if you make this infinitely rigid, the deflection in the rope will happen because of its own flexibility. Now, you all know how the springs in series are accounted for. So, if I have this spring having stiffness K1 and the other one with K2, if they are connected in series, we know that the equivalent stiffness is going to be K1 K2 over K1 plus K2. You can you must have studied this earlier, right. If these two springs are in parallel, they simply get added. Okay. So, if the springs are in parallel, then this is for the series case, and if they are in parallel, then they will be simply K1 plus K2. Okay. So, in this particular case, a simplified vibratory model will now be an equivalent stiffness, which includes the stiffness of the rope as well as the stiffness of the beam and the mass being load. That basically becomes the final simplified model. Okay. Here, because we do not know how to take care of multiple masses, we have restricted ourselves to a single mass system, assuming this winch mass to be negligible compared to the mass m, and of course, this beam's mass is also neglected. So, finally, one can find out a simplified vibratory model from this, and because we have seen how for such a simple single degree of freedom system, the natural frequency is given by square root k over m, and in this case its k is going to be k e, and that k e is going to be given by this expression, where k 1 is the k of beam and k 2 is the stiffness of the rope. So, k b k r over k b plus k r is the equivalent stiffness, and with that you can find out the natural frequency of this entire system. Is that clear? Now, the question is, how does it matter now? I mean, from the design perspective, whatever is the numeric value of the natural frequency, let us say it turns out to be 13.7 radians per second, or maybe So, let us say instead of radian, all right. So, we can have it radians per second only. How does it matter? Having some numeric value calculated, how does it matter? What will it, how will it help you in this whole design process? Okay. So, when we are learning vibration as a fundamental theory, we should always ensure that we learn to relate what we get through this analysis to the design process. Okay. So, Piyush, how will you use this information? How do I make use of the information that I get? Maybe as I said 13.7 radians per second, by substituting all these values I have got this value of omega n. How do I use this information in ensuring that my design in terms of all these cross sectional dimensions, the length I have chosen, the mass of this winch, maybe I may not be able to change it even if I am required to, but there will be certain situations or certain parameters which I may be able to modify. How do I use this information? So, please make a note that this drum may be rotating however slow it is, okay, and that rotation is going to create excitation to this system. This entire system is vibrating. Okay. So, if this motion and the associated fluctuating force because of unbalance or whatever other excitation function that it generates will create excitation to this entire system. Okay. So, you have to always look into the operation of the system and whether excitation frequency omega is anyway related or close to this natural frequency which I am calculating. It may turn out that it may not be exactly matching, but even if it is close enough, it would create lot of problems in terms of larger deflections rather than simple lowering operation that you find here. Okay. So, if this winch is operating or the motor is operating, if this winch is connected with a gearbox, if the gearbox is operating at a higher speed and if that speed matches with the natural frequency of this entire system, you should make sure that you adjust the parameters of this vibratory system, maybe make this thicker, reduce the length if possible. Okay. And so, making changes to the cross section of this beam is going to be much easier. Sometimes the mass may not be easy to change and so on, right. So, all the time when you get this response or the vibration features or vibration characteristic in terms either of its response or natural frequencies, this is something which we should immediately start looking at. How do I make use of this output in terms of better design of the system? Now, the next question that I have asked here is that is there a possibility that this system is a nonlinear system? Okay. Is this system a linear or nonlinear? Assuming that the amplitudes are well within limits, that means we are not saying that the amplitudes are large enough so that it becomes a nonlinear system, because we discussed this that if the relationship between the force and displacement, if that is not linearly related, then the system is not linear. So, k, the stiffness, if it is not a constant value, then the system is nonlinear. So, assuming that still at whatever vibration amplitude it vibrates with, amplitudes are reasonably small, even with that whether the system will be, is it possible to have this system to be nonlinear? Okay. Now, out of the assumptions that we made is that this is the stiffness of the beam mass of the pulley or a winch is neglected, and then you have this mass the stiffness of the rope and the mass. Okay. What is the expression that we use for the stiffness of the rope, where this L is this length. Now, when the mass is lowered or is being lifted up, this length is changing. So, your stiffness itself is changing. Okay. The only question is, when your oscillations are happening, if this length is changing fast enough compared to the time of oscillation, okay, then only the system parameter can be considered to be changing continuously. Okay. But supposing that this is moving way too slow, which typically is the case, it moves very slowly. So, if it is moving very slowly and your oscillations are maybe 10 or 20 oscillations already in that period of moving up. So, if that movement is slow enough, then you can treat the system to have constant parameters like K and M, right. Mass of course is constant, but supposing that this mass is you keep adding the mass to this mass being lowered or raised, the mass of course is constant most of the times, right. But if the mass being lifted up or lowered, if that movement is fast, then you may have to think whether the system has a constant Kr assumption valid, or typically I expect that the movement of this mass during the lowering and lifting up is moving reasonably slow. So, that the Kr can be presumed constant, but do make a note that the natural frequency that you obtain when the mass is completely at the top or when the mass is completely close to the ground, those two natural frequencies can be different, because the lengths of the rope will be different. Okay. Let us take this another example here, and it's solar panels of a spacecraft. So, these solar panels are can be seen on the circumference, and 4 of them situated at equal angle as you see here. The panels dimensions are all given here, their density is known. So, basically you can use this as a mass element, right, and they are attached at the end of this cylindrical rod, aluminum rod. In actual case, of course, you will not have them as rods, but they may be this kind of shape. You can have a look at some of these solar panels which are used, but I mean for the sake of an example, we assume that it is a simple aluminum rod. If that shape is different, you can as well find out from your solid models what is the stiffness of such structure. But assuming that there is an aluminum rod here at the end of which this panel are mounted, and these rods are connected to this body of the spacecraft. So, using these dimensions and the weight density, you can find out the mass property of the panel, and what is given here, that if the spacecraft main body, if it is assumed rigid, we are supposed to analyze this solar panel for its vibration characteristic, essentially to find the natural frequency of vibration. Okay. Now, how do you convert this physical system into a simplified vibratory model? Now, make a note that they are completely independent of each other. All these solar panels are all independent, right. So, we can treat one solar panel assembly as one vibratory system, and they are all identical vibratory systems in fact. So, how do I model now? What you would agree that if the solar I mean the satellite outer body, if this is assumed rigid, then I can use this aluminum bar to represent them represent as a spring, again assuming that the mass of that bar is negligible compared to the mass of the solar panel, and the mass of the solar panel is something which is at the end. Okay. And you can find out the parameters of this vibratory system K and M from the data given, right. So, this is again the simplest of the models that you can represent these solar panels and find out the natural frequency. Okay. Now, how do you find K? M of course is very simple, you have dimensions given, volume multiplied by the density will give you the mass. What about K? How do I find K? Now, again just like in the previous example, this can be treated like a cantilever. It is a circular member, and I can find out using this expression. Again you can refer to strength of material for the expression which is known, okay, 3 EI by L cube. EI is again the flexural rigidity of the circular shaped cantilever, L is the length. Okay. So, again there are some issues here, that what L shall I consider? Shall I consider only up to this point, or shall I take it from the center, and so on, right. But I can there will be assumptions involved in this case as well. I mean because the deflection beyond this point is not going to be strictly the deflection of a cylindrical piece. So, this L will be only up to this point, and then I can assume that this mass is completely at this location. Again this is going to generate values which are going to be slightly off from the actual value, but this is the first cut natural frequency value that we can get. We can make it more complex, more involved and take care of that, but as a simple vibratory system I can take this L to be the length of the cylindrical part. But the mass of course you can find from the dimensions, and I can use that mass to find out the natural frequency. But what stops this solar panel from vibrating in a torsional sense? Why are we only restricted to the bending vibration of this system, right? Because you may know that the satellite is positioned by by some internal mechanisms, like reaction wheel assemblies operate, and then they generate some kind of a movement which can excite the torsional mode of vibration. So, it is not only that this panel is going to vibrate in the lateral vibration or bending vibration, but it can also generate torsional vibration. Particularly look at the size of this panel. The panel size is going to have a reasonable polar area moment of inertia, a polar mass moment of inertia. Okay. So, this panel can generate significant twisting inertia or torsional inertia at the end of this cylindrical piece. So, there would be a polar mass moment of inertia I can represent, and then I can also get the torsional stiffness of the cylindrical part, and then I can, the way I can get the bending natural frequency, I can also get the torsional natural frequency of this system, where this is going to take the form like this. So, whereas this kT is the torsional stiffness, and last time we discussed how to find the torsional stiffness of any member. Okay. So, for a cylindrical member you can use the expression as T over I p is equal to g theta by L, which is involving the shear modulus of the material. Okay. So, and then you have T over theta as the torsional stiffness K T, and that is going to be right. G here is the shear modulus. modulus of rigidity. So, all these material properties and geometric properties, once they are known, it is all straightforward to find out the natural frequency. But now you understand, now this physical system you have to see and think about it as to how do I model this as a vibratory system. And as we discussed in some of the initial lectures, that a single mass and a single spring does not mean only one natural frequency. Okay. That mass and that spring together, in what mode of vibration it is oscillating, that will decide that the system, this mass may have all the 6 degrees of freedom. It may have this motion and the rotational motion, and therefore, you may have multiple natural frequencies, and for each of these modes you have to figure out and extract an appropriate stiffness term, appropriate mass term to generate the natural frequency. So, in this case, at the moment most likely natural frequencies to get excited are the bending ones and the torsional ones. Okay. Again, how can this information be useful to the designer? It can. So, it depends upon how the structure is. Suppose the structure is not symmetric, they will couple, just like in the blades which are there in the steam turbines, the blades are helicoidal, that means they are curved. So, you will less likely to get a pure bending, the bending will be always coupled with torsion. Okay. But let us not complicate the things at the moment, but yes, the bending vibration can get coupled to torsional vibration, then you will have a coupled bending torsional natural frequency. Okay. So, how would this information be useful to the designer? So that if there are equipments which are housed inside this satellite, which are operating at certain frequencies, they should not be run close to these natural frequencies, otherwise you will have amplification of this their vibration response. And as you know that apart from the material damping, there will be no other damping in space, right. Okay. So, this is how once you analyze a given physical system for its simplified vibratory system. Of course, we have not derived in each of these cases the governing equation of motion. Why? Because we are once we model this as a simple vibratory system, single degree of freedom system, since we have already derived the governing equation of motion and we know that the natural frequency is given by square root of k over m, we are straight away using it. But as a general case, you will have to then get the free body diagram and then generate governing equation of motion, and from that you have to get the expressions for the natural frequency, which is something which we will do later on when we migrate to a many degrees of freedom system. Is that clear? I hope this is fine. So, this is another example that I have taken for finding out basic natural frequency expression. The next example, which actually now focus on the response to initial disturbance. We have not seen or taken an example where the system is disturbed at t is equal to 0. Okay. So, of course, the example given you take your time to read through it. Essentially, it says that you have a overhead travelling crane, which you see on many of the factories, workshops. You will have an overhead crane which is supported at both ends. These are these are the walls on both sides, and in the workshop, if you want to lift certain things from the floor, the overhead travelling crane will do that job for you. This horizontal frame is assumed to be rigid enough, and then there are motorized system here which will again use the same kind of winch which we have seen in the previous cases, and we do not care now at the moment how this load gets lifted up and down. Okay. What is important is this entire system, physical system, how do I convert this into a simplified vibratory model. Now, assuming that this mass is located centrally to this platform, and I can then treat this entire system as a rigid body and treat it like a mass, okay, and the suspensions on either side of this travelling crane is treated like a spring. Okay. So, there are suspensions here which will have their own suspension stiffness K. So, if both of them are K, this equivalent spring is going to have a stiffness of 2 K, because both of them are in parallel. Okay. So, what we are doing is we are converting this physical system of overhead crane as a mass, and that mass is sitting over a spring. This spring has twice the stiffness of individual suspension springs here, and these wheels are rolling over rails which you can see here. These rails are on the platform here. I mean these are all at the these will be laid on a foundation. Okay. Now, the example that is involved is a section of the rail 6 meter long of the crane travel is improperly laid, as a result of which this section, okay, is 5 millimeter below the rest of the crane travel. That means, this crane is travelling like this, and suddenly a 6 meter long rail is improperly laid, and therefore, it gets shifted down by a small step of 0.05 meters or 5 millimeters. Sorry. Okay. If the train is if the crane is traveling at a uniform speed of 3 meter per second. So, here the motion of this crane is 3 meter per second. Determine the response of the crane during the period of travel when it goes on to this particular part of the rail, right. So, up to this point the crane is travelling without any vibration. So, it is steadily moving with a constant speed, and then suddenly this will drop to a lower height, because the rail is dipped because of the problems at the foundation, and we are supposed to find out the response during its travel in this particular section of the rail. Okay. Now, there are few assumptions involved. Of course, the first is the damping is neglected, and therefore, we can see that it is a simple spring mass system, no damper there, and we assume that this is the important assumption, that when the crane shifts from this particular rail to this particular rail, that the wheel suddenly goes down. Okay. That means, the crane falls on the depressed rail section as a sudden step displacement, that is important. So, the wheel does not simply bounce by certain distance like this. Okay. It simply from this point to this point, the movement of the wheel happens all of a sudden. Okay. That is the assumption involved. Okay. So, let us look at this example, that the initial mean position of the crane is this, and as it travels and encounters this sudden jump, the wheel immediately takes this position, but the mass will continue to travel along this line, is not it? It cannot just simply follow the wheel. Wheel is simply just touching the bottom part of this rail. Okay. Now, you all agree that this 6 meter long travel of the crane, what will be the mean position of this? Will the mean position be here? No. So, the mean position is going to be somewhere here, slightly lower. That lower mean position has to be same as the dip in the rail, right. So, that dip in the rail is let us say 5 millimeter. Okay. So, the new mean position is going to be 5 millimeter below the original mean position of the travelling crane. Now, what we have to do is to start looking at the response, vibratory response, assuming that the position at this point is going to be at t is equal to 0. Okay. And from this point onwards, how will the crane oscillate and what will be the amplitude of oscillation of that crane? What will be the expression of that response? We all know that response to initial disturbance is x cos omega n t minus phi I, where capital X is equal to square root of x naught square plus v naught by omega n square. That these expressions we have already derived, and of course, phi I is equal to tan inverse of v naught upon omega n x naught. Now, when you start the motion at t is equal to 0, when it suddenly dips and suddenly goes over this depressed rail section, what are these initial conditions? I am going to assume the response about the new mean equilibrium position as let us say x of t, and x is taken as positive upwards, let us say. Okay. What will be x naught and what will be v naught? Please make a note that the crane is travelling steadily with some speed and it does not have any vibratory displacement or a vibratory motion. Okay. So, will there be v naught? Please make a note, x naught and v naught are transverse to its linear motion, right. So, it is moving ahead at certain velocity at certain speed, and x is measured transverse, x is measured vertically up and down. Whether there will be any initial velocity to the mass of the crane. So, this is of course equal to 0 because there is no transverse displacement or velocity. Now, whether there is any transverse x naught? Yes, because instantaneously at t is equal to 0, the wheel touches the lower depressed section of the rail, but the mass stays here because of its inertia, and therefore, you may treat x naught to be equal to plus 5 millimeters. Okay. So, the mass stays there, the spring pushes the wheel down, and now you have a mass slightly at an elevated position at t is equal to 0, and that because x is treated positive upwards, your x naught or x at t is equal to 0 becomes plus 5 millimeters. Okay. And obviously, if v naught is 0, how much will be phi I, right. So, then x of t is going to be capital X. Now, capital X for v naught equal to 0 becomes x naught, which is 0 which is 5 millimeter. So, if we express all the responses in millimeter, then this is going to be 5. So, capital X equal to x naught equal to 5 millimeters. So, it becomes 5 cos omega n into t. Now, what is omega n? Square root of k over m, and that you can find out from the data given in the example. Okay. So, this response is with which the crane is going to move the moment it encounters that depressed rail section. Okay. So, obviously, 5 cos omega n t, please make a note that it is a cosine term. So, it is this is the usual position. So, from here, so it is going to be the cosine function is going to be looking like that. So, it will start with at t is equal to 0, it will start with 5 millimeter amplitude and then subsequent oscillations will happen at its mean equilibrium position. Okay. And the frequency of these oscillations is going to be omega n, which you can find from the stiffness and mass properties of the crane. Okay. Suppose as an extension to this problem, suppose the next rail section after 6 meter of travel is back to its original level, and I am interested now to find out what is the response in this section. What would I do? So, I will redefine my time here. Okay, t will be 0 in this rail section, but now the initial conditions will change. Okay. So, x naught, will it be minus 5? Because when it comes on to this rail section, the new level is going to be the original level of this crane, okay, if at all it comes to the original level. So, which means that if the crane is without any vibrations and moving like this, okay, then there will be a step change of 5 millimeter, but that 5 millimeter will be a compressed spring, right. So, it is going to be minus 5 millimeter as an initial x naught, and how much will be V naught? Will it be 0? Will it be 0? Of course, we have defined already that there is no damping. So, it is a undamped case. Okay. So, what we will have to do is at this instant of time, we will have to first find out what are the vibration because of these initial conditions. So, I will find out x dot t as minus 5 omega n sin omega n t, that is the derivative I get there to get a expression for the velocity, and for the new initial conditions, new in the sense when I am interested in exploring what is the vibration in this zone, I will have to take x at t is equal to 0, that is my x naught from these two expressions. So, now this is going to be for the new initial conditions, I will make use of these expressions for t is equal to how much time would it take for me to travel from here to here, okay, that I will get from my speed. So, if it is moving at 3 meter per second, okay. So, obviously, for a 6 meter long rail, time for me to get to the end of this section is going to be 6 by 3, that is 2 seconds. So, I will get this at 2 seconds, x at t is equal to 2 seconds. So, I will make use of 5 cos omega and whatever natural frequency that I have multiplied by 2. That will give me the amplitude at t is equal to 0 because of the vibrations during the travel on this particular rail. So, that x naught will be my vibrations at this particular instant of time, and I may not have any new V naught, but I will have the V because of the earlier vibrations. So, V naught for me is going to be x dot at t is equal to 2, which will mean minus 5 into omega n sin omega n into 2, that is basically V naught. So, to start with this x naught actually this x naught is not going to be minus 5, that x naught now is going to be minus 5 plus this value. And V naught, there is no new initial velocity encountered here. So, I can use the previous section's velocity at t is equal to 2. So, that is sin omega n into 2. So, these are going to be the new initial conditions for my travel of the crane in the third section of the rail, that is this section. Is that clear now? So, this is how you can find out the response of the crane during its travel, both during this period as well as during this period. So, vibrations will be different in the two sections. In the first case, we just took x naught as minus 5 for this particular case, because it was assumed that the crane is not vibrating before it reaches to that step section, and therefore, in that case we used x naught equal to 5 as initial condition, but for this particular travel or this particular section we have to take the vibrations at the end of this rail section to be considered or updated for the new initial condition starting from here for this section of the travel. Okay. That is how we do it. Okay, here is the summary of our lecture number 4. What we discussed is the undamped free vibration response to initial disturbance, right. So, the initial disturbance that we are talking about is the initial displacement or initial velocity that is imparted to the simple single degree of freedom system at t is equal to 0, and on on subjected to those initial conditions, what is the ensuing vibration response is what we discussed. We took some practical examples based on these concepts, and I hope this particular part is clear to you. Now, based on this, these are the recall questions that you should attempt, very simple and straightforward as such, and then you can review the answers that you got by looking at the answers given in the next slide.